Alright guys, so let's talk a little bit about friction. I know most of the course we've been ignoring its existence as much as possible, but now we're going to have to learn how to deal with it, so or at least at a very basic level. So to start off with, when you are working a problem that has friction within the problem, keep in mind that friction always opposes the motion of an object. So when you're drawing your free body diagram and the velocity of the object's in a certain direction, make sure that the force of friction is pointing in the opposite direction relative to that object's velocity. Now, as far as what this force of friction depends on, so we're talking about the friction that exists between, say, two surfaces that are in contact with each other. They depend on the normal force between the object and the surface. So in other words, that's the normal force is the force that is pushing those two surfaces together, or to be more specific, it's the force that the surface exerts back up on the object. And then the other thing it depends on is the nature of these surfaces, so the actual materials that those two surfaces are made out of. And to quantify that, to put a number on that interaction between the two surfaces and kind of how sticky those two surfaces are, we use something called a coefficient of friction. Okay, and when we talk about coefficients of friction for any materials, we're actually kind of referring to two different numbers. One is the coefficient of static friction. So when we use the coefficient of static friction, it'll be for a situation where the object isn't moving relative to the surface, but there is a force being applied to that object. If there's no force being applied to the object, then there's no friction. Okay, friction kind of appears as a counteracting force to some applied push or pull. The other type of coefficient of friction that we will see, come up is used when there is relative motion. So when one object is actually sliding across the surface, there's what's called a coefficient of kinetic friction. So the friction that exists between moving objects, and that is given the symbol mu sub k, whereas the coefficient of static friction is given the symbol mu sub s. Okay, so those are the two coefficients that will come up, and that's those are the two situations in which we'll use them. So how do we calculate this force of friction between the two surfaces? The equation to do it is fairly simple. So we say the force of friction, which will be in newtons as always. So this force of friction will be equal to our coefficient of friction, whichever coefficient we're using that's appropriate for the circumstance, times the normal force. Okay, so this is the force normal. This force will be 90 degrees relative to the surface and the object, laying on top of the surface. And that's really all it is. Okay, that is the equation to calculate the frictional force if you know the coefficient of friction between the surfaces and you can calculate the normal force between them. As always, it's also possible to calculate friction in terms of net force. So say it's kind of like the missing force of a vector addition. Those problems will come up occasionally, but even in the absence of knowing what the other forces are, you can still calculate what the force of friction will be. So to see how this works, I'll just take you through a fairly simple problem here. We have a force of 250 newtons, and that's being applied to a box that's on a table. The coefficient of static friction between the box and table is 0.5, whereas the coefficient of kinetic friction is 0.3, and you'll very often see that the coefficient of kinetic friction and the coefficient is going to be smaller than the coefficient of static friction. So the first question is, if the box is at rest, will the 250 newtons be great enough to cause the box to start moving? And really what this is asking is 250 newtons equal to or greater than this force of static friction that exists between the box and the table? So to figure out what that force of static friction is, okay, first let's draw a little picture here. So there's a 50 kilogram box. I guess I should define the mass of the box here. It is a 50 kilogram box. I just didn't say it. It's a 50 kilogram box, and we're having a force of 250 newtons, which I'll call my pulling force, being applied to it. And I want to know if it's going to start moving. So the first thing I need to do, if I want to calculate the force of friction, I need to know in this case the static friction, the coefficient of static friction since they're at rest, and I need to know the normal force. And the normal force that the table is applying to the box will be equal and opposite to the weight of that box. So to calculate the normal force, I'm going to calculate the weight of that box. Okay, so force normal will be equal to the mass of the box, which is 50 kilograms, times the acceleration due to gravity, 9.80 meters per second squared. And so for a normal force, I'll have 490 newtons, and that's the force I will use in my friction equation. I'll plug that in there. And we can see from this that the force of friction then would be 0.5 times 490 newtons. And again, just a reminder, this is because the box is at rest that we use the static coefficient. If it was moving, we would have to use the other one. So using that, we take half of 490, and we get sorry guys, we get 245 newtons. And so what we see from this is that the force of friction is 245 newtons. The force we're applying is 250 newtons. So since 250 newtons is greater than, well, in this case it's greater than, if it was equal to, it would also start to move. So since 250 newtons is greater than 245 newtons, the box will indeed start moving. So when it comes to the static coefficient of friction, that's mainly how it comes up. And it'll be a question is, will this start to move? Okay, will the object start to move with this given force? Now, if the object is moving across the table already, then what we need to do is we need to use the kinetic coefficient of friction, and we can use that frictional force to figure out net force, and from net force we can go back to the second law. So that's going to be a very common thing in this chapter is, okay, what's my net force? I know my net force. What's my acceleration? And relating those through the second law. So if the box is moving already, kind of do a free body diagram, we will have our 250 Newton force still being applied to it. We have our frictional force, okay, acting against it. We have the weight acting on it, and then we have the normal force, once again acting up from the table. The normal force will be the same as it was in the previous problem. So this normal force is 490 newtons. The frictional force, however, will be a little bit different because it is moving. We need to use our kinetic coefficient of friction multiplied by the normal force. So this will be 0.3 times 490 newtons. And so that force of friction will be 147 newtons. So let's take into account our coordinate system. Let's make to the right positive. And so our net force here will be equal to 250 newtons plus a negative 147 newtons. It's negative once again because the friction is opposing the motion and it's pointing to the left. And so our net force for this will be 103 newtons. Okay. Now, knowing the net force, what we'll do is we'll use the second law to figure out our acceleration. So if net force is equal to mass times acceleration, acceleration will be equal to net force divided by mass. So we get 103 newtons divided by our mass of 50 kilograms. And so we would have an acceleration of 2.06 meters per second squared. Okay, and that would be our answer. Okay, so friction is just another force, guys. It's another, it's a type of contact force. It does have an equation that we can use if we know the coefficients of friction to calculate it. But these problems will end up being, very similar to what we've been working in that, we'll figure out a net force to get an acceleration. If we have an acceleration, we'll calculate the net force from that. Knowing acceleration, we can use kinematics. Okay, but the second law is still kind of the central theme here, and we'll keep on returning to that to bridge these forces and the accelerations that objects will be experiencing.